The most typical form of stimulus and response for DNS is a simple request to a server that knows the answer to the question we have. So this is very simple. We have a DNS client, a DNS server. And remember, this is essentially a database transaction. So we're asking a question to get an answer, which is basically querying the DNS database. In this case, we're sending a DNS request for the A record of server 1. Remember, an A record is the DNS message type associated with an DNS name to IPv4 address mapping. So we're saying we want the A record for server 1, which means we want the IP address. Ask as a normal question, we would say, hey DNS server, what is the IP address you have on record for server 1? The DNS server is going to receive this question and respond with an answer, and it's going to say, server 1 is 192.168.1.5. It's going to provide the full content of that A record. Now, if there were multiple addresses here, it would provide all those. In this case, there's just one. So server 1 is 192.168.1.5. Pretty straightforward. Now, one thing we haven't mentioned at this point is caching. It doesn't make sense if every time you go to google.com or every time you went to server 1 that the DNS client would have to redo this query. So the DNS client will actually cache this information for a certain amount of time. And that means that it won't that it can rely upon that cache for at least for a while up until it needs to query again to get the new information, and that's in part related to the information that comes back from the DNS server in terms of how long it does that. But that's important to note here that that's a normal part of SNR. So if you go to google.com, see this DNS request, wait a couple seconds, go there again, and don't see any DNS request, that's why is that response has been cached. And generally the DNS client, which is your workstation or endpoint system, is going to take the quickest route it can to getting the answer it needs. And if that's in the local cache, that's where it's going to go. I've opened up a file now called dnsqueryresponse.pcapng, and it's basically the manifestation of this example we just talked through, wherein we have a very simple DNS query and a response that comes back. In this case, this was captured from the client's perspective, so from the person initiating the request. In this case, I was browsing to Wireshark.org, and you can see that over here in the info column, Wireshark.org. And before I could actually do that and make my GET request via HTTP, I had to perform a DNS lookup to get the appropriate IP address of Wireshark.org. Now, in this case, a couple things. First of all, we'll see this was sent from the source 192.168.0.114 to the destination 205.152.37.23. In this case, that was the DNS server that I was communicating with, and it was not a local DNS server. It happened to be one out on the internet somewhere. So fair enough. Now, if we look down here in the packet details section, we see a couple interesting things. First of all, I mentioned this, DNS relies generally on UDP. So we see UDP here. There are a couple instances in which DNS will not use UDP. One of those are when the response size is larger than a specific threshold. The other is when zone transfers are in place, which is also a sizing issue where reliability really matters in that sense. But for the most part, otherwise, DNS is going to rely on UDP, and it's going to generally be on UDP port 53, which you see right here. So that's the standard DNS port in this case. Now, if I expand the DNS section here, we've got some interesting stuff going on. First of all, we have this transaction ID value, and this is a concept we should be getting familiar with all the protocols we've looked at this point, is when you have a transactional protocol where you have queries and responses, you need a way to tie those together, and the transaction ID is how you do that. In this case, we see the transaction ID is 180F. If I go to packet 2, which I know is a response, we see we have the same transaction ID, 180F. So that's how these are being linked together. These two packets, this question and answer, this query and response are linked by a transaction ID field, similar to many other protocols that we've seen. Now, the purpose of this packet is really defined in this flags section. We have a couple different things going on here. It sums it up for us and tells us that this is a standard query, which we also see up here in the info column. But we know that because specific flags are set. This first flag here, all the way to the left, is set to 0, which is how we know this is a query in this case. Now we have a couple other things that are here. For instance, we see that recursion is desired. We talked a little bit about recursion. We'll show a more practical example of that here in just a moment. But this is where different settings define some of the characteristics of the DNS packet. Those are the only ones we're concerned about quite right now. So I'll go ahead and collapse that back down. And now we see we have the questions and answers information. We see, remember, we have a section that tells us how many questions there are, how many answers there are. In this case, it tells us there is one question, no answers. Now, note here it says answer RRs. We haven't talked about RR. RR stands for resource record. When we talk about DNS as a database, a mapping, a DNS mapping, domain to IP, for instance, an A record, RR stands for resource record, and that's specifically referring to that database entry. So a resource record is a database entry in DNS parlance. So think of it that way. Now, in this case, it tells us we have one question, no answers, and that's it. Below that, we should see the question itself, right? We have one question, we need to see that question, and that's located in this query section, which is what's going to round out the DNS packet. I can expand that, and we'll see the actual query. In this case, it's a query for, or a question for, Wireshark.org, and it's for a type A record. Remember, type A is a DNS hostname to IPv4 address mapping. So that's what we're looking at here, is this query for Wireshark.org. Now notice down here below, DNS is a clear text protocol, so we can actually see that listed here. We see Wireshark.org in that. Makes it really easy to dissect DNS packets. Now if I go to the response, we should expect to see an answer for this question. And sure enough, we do. We see one answer resource record here as well. But notice too, we still see one question, right? And that's because the response is actually going to reflect the question back. It's going to include the question back with its response. And you see that here because we still have the query. The same query we saw in packet 1 is also in packet 2. That's included. And then what we have here though is a new answer section. And that answer section is actually going to have the information we need. In this case, we see Wireshark.org. We see that it's an A record. And down here below, we see the address 128.121.50.122. Now, a couple other pieces of information here. Data length tells us how long the address is, in this case 4 bytes. We also have time to live, in this case 14,400 seconds. And that time to live relates to how long this query response is good for, how long this can exist in the cache of the client system before it needs to recreate a new DNS query. So this is our answer. Again, we have it paired with our question in this case, so you can actually look at a DNS response and get the information you need. You don't always have to look at the query itself, so that's pretty cool. If someone had a knife to your throat and said you need to figure out this DNS problem, but you can only have the query or the response, which do you want? You would say the response, because that actually includes the query information. Now, if you've gotten into a situation where someone is holding a knife to your throat, asking you to solve DNS problems, I think you may have bigger problems, and maybe this knowing how to analyze DNS is maybe not it. But nonetheless, this is our example of DNS. Very simple DNS transaction, a question and answer, or a query and response, depending upon the terminology you use. Once this is completed, our source system, our 192.168.0.114, knows that Wireshark.org is at 128.121.50.122, and it can initiate an HTTP transaction if it so desires. The next type of stimulus and response I want to go through is DNS recursion, and that's something we've talked about a little bit already. In an ideal situation, in the situation we just looked at, we saw that a DNS client goes straight out to a DNS server and asks a question, and it says, hey, what's the record for this host? Give me the IP to host mapping, and the DNS server will provide that back. But DNS is a hierarchy, and each DNS server is responsible for its own zone. So what happens when you need to get an answer from a zone that your DNS server does not provide, right? So when we think about DNS architecture, generally in most networks, you have hundreds or thousands or tens of thousands of computers, and they generally go through a local DNS server on your network to query things, right? They have a central kind of funnel they go through to talk out to the internet via DNS. They'll always start with the local DNS server to ask questions, get answers, because most of the things they're going to need are inside the network. But when they need something else, they'll ask that DNS server, and that DNS server will have to go out to the internet and get information and get the answers you need via this recursion process. Now, there's reasons for that, right? Just as a local DNS client, so your workstation will have a DNS cache to prevent the number of DNS queries you have to make, the DNS server will as well. So whereas if you had 10,000 computers on a network and they were all going to google.com, and if they're all going straight to the internet, they might have to all query DNS independently. And that would take up a lot of internet bandwidth. If you have a single DNS server, once it queries upstream and finds the appropriate mapping the first time, that appropriate DNS resource record, it's going to cache that itself. The DNS server also has its own cache. So all those 10,000 hosts can get their answer from the DNS server within the network without having to go across the internet. So that's one of the reasons it's architected that way. It's another efficiency thing. Now, in this case, for our example, we want to talk about recursion, which is when the DNS server doesn't know an answer. Now here we have a DNS client and it wants to know the A record for a server called Mayfield FS, Mayfield File Server. So it's communicating to its own DNS server. In this case, its DNS server is in the wonderful city of Lexington because they're in the Lexington office. Unfortunately, the DNS server in Lexington is only authoritative. It only knows the mappings for its own zone, all the systems within Lexington. It doesn't know the information about the systems in Mayfield. However, it does know how to communicate with the Mayfield DNS server. This could be something that was dynamically configured out, or maybe it was something that was statically put in. You can statically configure a DNS server to know which upstream servers to talk about, or to know which networks are, which servers are authoritative for which networks. So in this case, the DNS server, when it receives the question from the DNS client, is going to take that and repackage it. And it's going to repackage it and send it to the DNS server in Mayfield. So Mayfield's DNS server is going to be authoritative for that zone, so it's going to know the answer. It's going to have the appropriate database record for Mayfield FS, and it's going to respond to the DNS server with the answer to the question. It's going to say Mayfield FS is 192.168.1.5, at which point the DNS server in Lexington will take that answer and then provide it back to the DNS client. Now, the interesting thing here is you're only going to see parts of this communication depending upon where you capture packets. If you capture packets on the DNS client, you're only going to see the first request and you're going to see the response. So you're not going to see any of the stuff on the right side of the screen. You'll only see the recursion, or excuse me, you won't see any of the recursion. You'll only see a request to your DNS server and an answer based upon the way this is divided. And that's important to note when you're capturing DNS traffic and you're trying to figure out what's going on. If you see a request go out but never see a response come back, you don't necessarily know if that's a problem with your DNS server or a problem upstream related to recursion. So you may have to actually capture on the DNS server itself. If you captured, in this case, on the Lexington DNS server, you would see all 4 of these packets going across. On the flip side, if you captured only on the Mayfield server, you would only see the request from the Lexington server and the response back to it. You wouldn't see anything from the initial DNS client in this case. So important point to know when you're digging through packets or you're trying to capture packets related to DNS recursion. To illustrate the concept of DNS recursion, I've opened a file called DNS recursive query client.pcapng. Now, this is a packet capture that was created from a client doing a DNS resolution. In this case, you see we have a source of 172.16.0.8. That's our DNS client. And we have a destination of 172.16.0.102. That's our local DNS server. I've told it to do a query to nostarch.com. So I'm actually going out to the No Starch Press, the publisher's website. I've typed that into my browser, hit enter. I don't know what the IP address is, so I've initiated a standard query for nostarch.com. In this case, we see a response back from our DNS server, 172.16.0.102, to our client, 172.16.0.8, with the answer. And we see, without even digging into the packet, we see standard query response, nostarch.com is 72.32.92.4. So we got our answer. But I'll tell you, this client does not exist on the NoStarch network. The DNS server 172.16.0.102 is not authoritative for the NoStarch zone or the www.nostarch.com zone. So how did we get this answer back if it's not authoritative? How did this happen? Well, the answer, of course, is recursion, but we can't see that here. And the reason is because this was captured from the client. Remember, when you capture from the client, you don't see the recursion process because it's all happening upstream. It's happening upstream of the DNS server, so we don't see that. So let's actually take a look at this same capture, but from the perspective of the DNS server. I just so happen to have the DNS server capture pulled up here as well. If I can get it open here. Here we go. So now we're looking at DNS recursive query server.pcapng. And what I did here when I did this, when I initiated this query, was I actually had a packet sniffer going on the client and on the server at the same time. So you're actually seeing the exact same traffic just from 2 different places, which is a really cool way to look at things. And of course, now we have 4 packets. So we see 172.16.0.8, that's our DNS client, remember, and we see 172.16.0.102, that's our local DNS server. So we see that query go out. But instead of seeing a response immediately, we don't see that response at all. Matter of fact, that response is now in packet 4. We see an intermediary process going on here. In this case, our DNS server, the device ending in 102, did not know the answer to this query, so recursion had to occur. Now, how do we know recursion is allowed to occur? Well, if I expand this DNS query and go to flags here, we see we have this option called recursion desire. If this is set, that means recursion is allowed, which basically says, hey, DNS server, give me the answer to this question. But if you don't know it, go out and get it. I really need to know. If this was set to 0, recursion wouldn't happen, and the DNS server, if it didn't already know the answer, simply just wouldn't be able to provide it. It wouldn't have that particular answer. So pretty neat. Now, if we go down here, we can see that the second step of this process is our DNS server, the device ending in 102, is actually going out to a server on the internet, 4.2.2.1. It's a very popular open DNS server that folks can use. So you can actually point your system right now and resolve DNS via 4.2.2.1, something a lot of people use. So we're going to an upstream DNS server in this case and saying, hey, how do I get to nostarch.com? That means this server, this 102, is configured to have 4.2.2.1 as its upstream DNS. After that, that device responds, 4.2.2.1 responds to 102 and says, hey, nostarch.com is at 72.32.92.4. So it's actually providing the answer, at which point we see the DNS server, 102, provide it back to our client. So we're going from client to server, from server to upstream server, from upstream server back to DNS server, from DNS server back to client. So we have 3 devices at play here. Now, the interesting question is, does 4.2.2.1 actually know the answer? Is it authoritative for nostarch.com? Well, no, it's not. It's actually doing the same thing. It's doing recursion as well, but we can't see that because we're downstream. If we were capturing packets in 4.2.2.1, we would see the traffic coming in from 102. And then we would see whatever 4.2.2.1 does next, where it goes upstream. So we would see immediately downstream, immediately upstream, and that's it. And that's the key point is anytime you're on a DNS server and recursion's happening, you'll see the inbound query, you'll see the outbound query, and you'll see 1 degree up and down. You won't see any more than that, which can make DNS issues a little tricky to troubleshoot if you need to trace that whole train, especially if you have multiple DNS servers on your network. But for the most part, the recursion concept isn't too hard. It's just basically saying, hey, DNS server, if you don't know the answer to my question, query upstream until you can find it. And that's really essentially how DNS architecture works across basically the entire internet. Thus far, all the examples we've looked at of normal stimulus and response are such that we're actually looking up domains that really exist. But one of the things that is going to happen really often is you go to type in a domain and maybe you fat finger it, maybe you enter the wrong key, and you type in a domain that is non-existent. So that's normal stimulus and response, and we need to understand to some degree what that looks like when you try to execute or try to browse to a website or browse to a domain name that doesn't exist, and DNS can't find a record matching that name. Now, for the most part, all the processes are going to be the same. We're going to have a DNS client, a DNS server, and we're going to have a DNS client that tries to resolve a name. That's going to be the first step. Let's say we're browsing to a website. We're trying to browse to can'tseeme.info. I don't know if that actually exists. I just made that up for this exercise. But in this case, we'll say it doesn't exist, and I've attempted to browse to it. So the very first thing that's going to happen is that DNS request, so we can map the domain name to the IP address. Now, our client is going to send that to our server, and assuming recursion is allowed, our server is going to go out and try to find an authoritative name server for that specific domain. Now, in this case, if this domain doesn't exist, it's not going to be able to find one. So what's going to happen is it's going to get a response back from the server, from its upstream server, saying that there is no such name, and that's what it's going to pass back on. So from the client side, we'll see a DNS response come back with configuration bit set flags set that say there is no such name. So there will come back a packet with nothing in the DNS response or answer section, and at that point, the client is out of luck because we can no longer find the domain, and the browser will handle that however it's expected to handle that. That's going to be a little bit different per browser, but it's all going to be contingent upon getting this no such name response back from the DNS server. Back over to our packets here, let's look at an example of this in the file DNS query nonexistent.pcapng. In this case, I've actually gone out and queried for a domain name that I was pretty darn sure didn't exist. You see up here in the query section, I queried for 12498. I just basically mashed my face against the keyboard and typed in a bunch of numbers and then put .net. I was pretty darn sure this wouldn't exist, and it looks like I was actually correct. In this case, my source, the machine I did this from, was 172.16.16. 18.170. It was configured to go directly out to a DNS server that exists on the internet, in this case 8.8.8.8, which I believe is a Google DNS server. And what do you know? There is no domain that resolves to this. That doesn't exist, a domain that exists. So we got a message back that says standard query response, no such name, right? So pretty neat. That's what we would expect based upon what we talked about. But let's dig into this here. Now, the query for the most part is a standard query. Everything we expect to see is here. We see we have one question. We can expand that query, and we see it's a query for a record for this particular domain name. Let's look at the response, because that's where things are going to be a little bit different. I've expanded the flags section here. Well, first of all, I've made sure the transaction ID match, F23F. That matches the transaction ID of the first packet. So we know these are a pair. Also, Wireshark kind of gives us a little hint here that tells us the request is in frame 1. Now, for flags, I've expanded this here, and it tells us, if we go down to the bottom here, the reply code is no such name. So we know by looking at that we're not getting a response back that's going to give us the information we want. We can further verify that by looking here that we have no answer resource records. Our question is answered back, but we have no answer resource records. Now, we do have an authority resource record, and that's an authoritative name server. It's the one who we've queried to find out where this DNS record would be. In this case, it's a start of authority record for a global top-level domain server, a.gtld-servers.net. There's going to be one of these for every letter of the alphabet. That's how that hierarchy is organized. And we've queried this. We've queried a.gtld-servers.net, and it's told us that it's not aware of anything that meets this criteria. We see that it's related. Looks like it's maintained by VeriSign here. We see there's some interesting information. We have retry intervals, expire limits, minimum TTLs, a few other bits of information related to start of authority records, which we haven't covered in detail. Not super important for this example. What is important is that we don't get any answers back. That's the important thing. So when you query something that doesn't exist, you should expect to see up here a no such name, and that's what's going to signify that you've queried for a DNS record that doesn't exist, or some type of infrastructure that is responsible for serving that DNS record back to you is not accessible for some reason.